Hello.
Over the same field.
Over the same field.
Yeah, yeah.
But now only
Let us start with a very promising talk by Sokolov, who is going to tell us about this cutting planes lower bound for random CNFs, which was a breakthrough result a couple of years ago. But supposedly you have a new proof or something new. And no, I'm sure he has. Well, let's see the proof. So this is going to be until 1 hour. Yes, thank you.
Thank you. Yeah, thank you for the introduction. Yeah, unfortunately, like I claim the known results, so I should present something new. And I'm going to present the whole proof of this result, actually. And I'm trying to do it in 1 hour. Well, it will be some technical talk that I usually don't like to do, but what else I can do in this situation? Okay. What are we doing? You have proof systems, and in general, it's some algorithm that checks if some X live inside language, and we have like a witness for it. So, and our polynomial algorithm just check these witnesses or proofs. And usually we study some specific proof systems. The most famous proof system is resolution. So our language is the language of unsatisfiable CNF formulas. And what can we do in resolution? We have our formula, and the witness is a sequence of clauses. And how the sequence is generated. So we can pick any clause from our formula. And we can use resolution rule to produce new clauses. So we can, if we have two clauses of this form, then we can produce one more clause. The idea, if we have satisfying assignment for these two clauses, then we have the same assignment will satisfy the resultant, so the result of this operation. And our goal is to derive an empty clause that is not satisfied by any assignment. Usually think about this sequence as about a direct acyclic graph. So if we use this resolution rule, then we can draw two clauses as predecessors and the result as a successor in our direct acyclic graph. But today we are going to talk about more complicated proof system, cutting planes. So instead of just clauses, we can deal with linear inequalities over integer numbers. So sequence, so the proof is the sequence, but sequence of inequalities. And how we generate the sequence. We can start with some encoding of clauses of the formula. And I'm going to deal with semantic rule that says that if we have two inequalities, then we can derive any inequality that semantically follows over integer numbers. Here should be -1. So our goal is to derive some inequality that is trivially unsatisfiable. So our goal is to derive inequality that says -1 is bigger than 0. Okay, and it is powerful proof system. We know not so many lower bounds for this. And in particular, it's stronger than the most famous resolution proof system. So if you have a short proof here, then we also have a short proof here. Any questions or comments? What do we know about proof systems? We have lots of interesting proof systems, and for few of them we can prove lower bounds. So this is resolution proof system. This is cutting planes proof system, and arrow means that this proof system is stronger. So here we have shorter proof than in this proof system. Well, we have like really strong proof systems like Frege, that our usual proofs that we produce, and we have like very strong proof system like ideal proof systems and quant proof systems, for which we have no idea how to prove lower bounds. And here is some line. Below this line we know lower bounds. Above this line, not now. Okay. Of course, our goal is to produce lower bounds for all proof systems at the same time. It will give us in particular the result that in P is not equal to co in P. That is interesting for everybody, but current situation is not so optimistic. We don't even have candidates to candidate formulas that will be hard for all proof systems. And why we have a problem with candidates? Suppose we have an unsatisfiable formula, and we know that this formula is unsatisfiable. Of course, there is a proof how we trust each other that this formula is unsatisfiable. And unfortunately, if we can prove to other person that this formula is unsatisfiable, we can formalize this proof in some proof system. Well, it's not like a formal statement, but it's a situation that we have. So, yeah.
What is, I think, Jan was on top formula, the one that satisfies that something is not in the range of the function.
Yeah, that's what I'm going to say right now. So, another idea how we can create hard examples are distribution on formulas. We don't pick like some specific formula. We pick some distribution over some formulas. It's fine. We do not have counting argument in proof complexity. So we cannot do the same trick as we have in circuit complexity, like we count number of functions, count number of circuits, and produce that, oh, on average, some circuits will, some formulas will be hard for all proof systems. No, it's not the case, because like number of formulas is approximately the same as number of proofs. And based on this idea, we can develop some candidates. First is random delta CNF formulas. So we just pick random CNF formula and we generate some clauses. And if we generate enough clauses that with high probability formula will be unsatisfiable. And the conjecture that no proof system can certify that this formula will be satisfiable on average. Second candidate is clique formula. So again, we have a graph and we distribution on graph. So we Erdős-Chernyi distribution, and if we have like right density, we can ask about if there is a clique inside this graph, and the conjecture that no proof system can certify clique formulas. And the last candidate is exactly you all asked, is pseudo-random generators. So we have some function and we pick some point outside of the image of this function. And we ask our proof system to certify if this point inside the range of this function or not inside the range of this function. I will formulate some open problems about pseudo-random generators in the end of my talk.
what is the probability?
Well, we have, so suppose we have like claim that for some density, we do not have a click. And for some density, we have a click. And if we pick density around the threshold, but like below, a bit below threshold, so with high probability, there is no click. But we ask about of certain signs. But here we ask our proof system to certify the existence of click, and probably the hard statements that click have size around n to the epsilon for some small enough epsilon. More questions? Yep.
Are the truth table tautologies an example of pseudorandom generator formulas?
No, so it depends on encoding.
Okay, thank you.
Today we are going to focus on random delta CNF formulas. So what is it? We have n variables and m clauses. So we pick for each clause we pick delta neighbors uniformly at random over all possibilities, and we choose negations uniformly at random. So we have some nice parameter clause density. And we know that if clause density is big enough, then our formula will be unsatisfiable with high probability almost 1. There are lots of motivations why these formulas are interesting for us. I said one that this is a candidate to be hard in all proof systems. Another motivation that is speech conjecture, that there is no polynomial time algorithm can prove unsatisfiability of constant size random CNF formulas. And if you know this conjecture, that under this conjecture, we can prove non-approximability results for lots of natural problems. Here a picture that we have in the beginning. But what do we know about random formulas? Well, line is the following. For resolution, polynomial calculus, sum of squares, Nordström proof system, again, we know everything, and it's in some sense the canonical example of hard formulas for these proof systems. For cutting planes, we know something. We know that if our delta is log n, not constant, it should be like big, then we can prove lower bound. But for constant random CNF formulas, we cannot prove anything. KDNF resolution proof system, it's also a borderline. So we can prove lower bound for some parameter k that is below reasonable thresholds. There is some gap. There are some natural thresholds in k, and for k really below this threshold, we can prove something, but for some case, we cannot prove anything. And this is one of the important open problem in the whole proof complexity, to prove lower bound on random CNF formulas in AC0 Frege. In my opinion, we really need to develop like completely new techniques for this problem. Okay, more questions, comments? Well, I promised to present you the full proof that random log n CNF formulas are hard for cutting planes proof system. So, how the typical strategy works for cutting planes? We have our Boolean formula, and we create some function, some monotone function that is associated with this Boolean formula. And this strategy was used in lots of papers. So it was more or less originated by Impagliazzo, Pitassi, Urquhart. and by Krajcik for restricted versions of cutting planes. First full proof of the results for cutting planes was done by Pudlak. And all of this paper utilized this idea that we have some function that is associated with the formula. These two papers are papers where the log n there was proved lower bound for random log n CNF formula. And they also used this idea where we create some function that depends on formula. And what can we do with this function? It's monotone function, and we want to prove monotone circuit lower bounds for this function. And how we usually prove monotone circuit lower bounds? So in the original paper, it was interpolation, approximation of clique function. So from some formulas, we extract clique function, and we prove monotone circuit lower bound on clique function. And the size of monotone circuits related to the size of the original proof in cutting plane. So if our formula is, if our function is hard for monotone circuits, then the result, then the formula was hard for cutting planes. In fact, we need to deal with real monotone circuits, but let me omit this part for this talk in order to avoid some problems. Okay, what we are going to do now? In fact, in all of these papers, there is some intermediate step. It either implicit or explicit, but in all of this paper, it was used in some sense. That we have reduction from our formulas to some communication problem for non-standard model, so-called DEG-like communication model. And after that, we have a reduction from DEG-like communication model to this function. Okay, and this step is more or less trivial. It's straightforward. If you have, I have not yet described this model, but I will. But this step is trivial. If you have proof of this formula in cutting planes, that it immediately gives us some DEG-like communication protocol for some communication problem. This step in some sense is easy, and in some sense is hard. We always have a trivial way how to get this function. But in order to prove monotone circuit lower bounds, we need nice description of this function. That makes this step not so easy anymore. So to produce nice description for function, it's a non-trivial step. Today we avoid these problems, and instead of producing any function, we just do bottleneck counting for DEG-like communication protocols. That is easier than Yukna's criteria that was used here, and at the same time, we even don't need to think about the function that associated with the formula phi. Any idea? Any comments, questions? What is the communication problem, and what is the DEG-like communication? At first, I want to describe communication problem. It's pretty standard for proof complexity, unsatisfiable closed search problem. We have some Boolean formula of two types of arguments. It's unsatisfiable Boolean formula, and Alice gets some assignment to X variables, and Bob gets some assignment to Y variables, and their goal is to find a clause that is not satisfied by their assignment. That makes sense? Good. We assume that we deal with balanced CNF formulas. That step was used before also. So we assume that in each clause, approximately half of variables belongs to each player. Usually we distribute variables uniformly at random between players, and with some technicalities after, we can easily reach this condition. Well, approximately half means that if we distribute 1/4 to each player, it will be fine for us. Any constant. The main reduction that we want to use today is that if we have cutting planes proof system of size S, then cutting planes proof of our Formula 5 of size S, then we have DAG-like communication protocol for this problem of the same size. Yeah, in interpolation, implicitly use this fact inside the technicalities. Yeah. So interpolation may be reformulated in these terms. And in Krajcik's paper, he did it implicitly for resolution and for cutting planes with bounded coefficients. In Pudlak's paper, he did it for more complicated versions of the protocols, also implicitly, and in my paper, it's written explicitly. And what are the DAG-like protocols? It's a generalization of usual communication protocols, but in a little bit weird way. We have a directed acyclic graph, and we assume that our degree of each node is at most 2. And we associate some set that is subset of product of Alice's inputs and Bob's inputs. We associate this set with each node. With the root, we associate the whole product. And we have some covering property. If we have this set for predecessor, it should be covered by union of sets of the successors. And in the leaves, we have sets that are marked by common solution for our problem. So in the lists, in our case, if we deal with unsatisfied closed-stage problem, here we have sets that corresponds to assignments that do not satisfy specific clause. So any point from this rectangle. So point has 2 coordinates. First is an assignment from Alice's side, and second is an assignment from Bob's side. And any point from this rectangle should not satisfy some specific clause. So we will call it monochromatic rectangle. And today we're going to deal with rectangle communication protocols. So we assume that each set at each node has this form. It's like product of some inputs on Alice's side and product and some inputs on Bob's side. In fact, for full version, we need to consider more complicated structure here, so-called triangles, but let's omit these technicalities today. Everything that I will present also will be true for triangles, but I need more time to convince you in this case. If you're not familiar with these DAG-like communication protocols, you can use this translation. So suppose we have our cutting planes proof, and here we have some inequality of this form. Here we have inequality of this form. And the set RH will be, so we want to transform it into communication, DAG-like communication protocol. And we transform it in the same DAG. And we want to associate here some set RH and this set RK. And the set Rk will be a set of all points that do not satisfy this inequality. This is it. That's how we transform cutting planes proof into DAG-like communication, but for triangles. I'm gonna simplify the strategy a little bit and deal with rectangles. Yeah. Any questions about DAG-like communication protocols, or everything is clear?
Common solution for all issues.
That means that we're going to use these protocols to solve communication problems, like for these communication problems specifically. That means that for any point in the leaf of our protocol, so here we also have some rectangle associated with this leaf. And a rectangle, any point here, so has some coordinates. So it's a point AB. And that means that for any point from this rectangle, we have one specific clause that is not satisfied by any point here. So we have one solution for all points. It's like in classical tree-like communication. If we reach the leaf, we know the solution for our communication problem. More questions?
Yeah. So you're using you're going to present with rectangles instead of triangles. Is
Yeah,
this the same as you as the real monotone?
Yes. Yeah.
It's the same.
It's the same as real monotone versus Boolean monotone. Yeah, this is the only difference. More questions? Proof idea. We have our DAG-like communication that we use for unsatisfied closed search problem, and we're going to create some mapping new that maps all, not all, it's still with partial mapping, that maps some of Alice's inputs and some of Bob's input to some specific nodes into our DAG-like protocol. The domain of this mapping will be like large enough. So we will map at least constant fraction of all possible inputs. But at the same time, we will prove that our mapping, we cannot map too much different assignments to Alice and different instances to Alice and Bob to the same node of our protocol. If we combine these two properties, that means that we should have lots of different vertices. We should have at least 2 to the f of n different vertices in our communication protocol. The only problem how to define this map. If we will define this map, we will prove lower bound on our DAG-like communication protocol. That will also give us lower bound for cutting planes proof. And the idea, in some sense, ideologically is the same as we have for widths in resolution proof, but in some sense it's 2-dimensional widths. But it's not like really easy to fit. So we want, with some input, we want to associate some vertex, and this vertex should be as close to leaves as possible, such that this rectangle that associated to this vertex contains some useful information about X. It's like general idea. Now I'm going to describe what does it mean, the useful information. Let's consider some rectangle, and we pick some point x0. It's a point from Alice's side. So we have full horizontal line, and we have this part of this line. It's an intersection of line x0 with our rectangle. We have some covering of this part of the line with monochromatic rectangles. These rectangles corresponds to leaves of our protocols. These rectangles means that we have some specific clause that is not such that any assignment from this rectangle do not satisfy specific clause in our formula. So we consider some covering of this line by these rectangles. And we can define some width measure for with two parameters. This measure depends on x0, and h is a point in our, it's a node in our, yes? Oh, sorry? Oh, we fix some node in our DAG-like communication, h. We have a rectangle that is associated with this node, and we pick some x0. It's just a point from Alice's side, and we can consider covering of this intersection between the horizontal line that corresponds to Alice's input and the rectangle. We consider covering with monochromatic rectangles.
So these are like the leaves that would be below this node H, for example, or some subset of those leaves, for example.
Are they the leaves or are they from the original formula?
From the original formula, but it's the same since we have DAG-like things.
Yeah, sure, but you can always expand it.
Sorry.
Keep going, I'll let you support.
Okay. Anybody have more
Wait, did
questions?
you finish? Sorry.
Okay. So we want to define the measure, width measure for x0 at node h as a size of minimal monochromatic covering for this line. So in this case, it will be like 3. So if we do not have smaller covering for this line.
Do you consider covering rectangles from the protocol?
Yes.
From leaves of the protocol.
These are leaves of our protocols here. So it's monochromatic rectangles that do not satisfy some specific clause. Yeah. Okay. Now we want to pick some parameter k. It's not clear why it should be like this, but let's pick it. It should depend on the structure of formula, but for our purpose, it's enough to deal with this parameter. And we want to.
Following on Robert's question, so this minimum automatic covering, I can just think of clauses of the formula that cover this number.
Yes. Yes. Exactly. And we want to put x0 into the lowest node in our DAG-like protocol with huge measure. It's not like this. Let me fix this definition a little bit. So we start from leaves to root, and for each vertex, we consider all possible axes that has large measure into this node. We put these instances into this node, and we erase these instances from all protocol, from all rectangles into this protocol. We completely erase it from our universe. We do the same with Bob's side, and also erase everything from our universe. So it may affect the measure. So the measure can decrease for future instances. And we go and we repeat this process. So what do we know about this process? At current node, before we do this this operation, we actually know that measure of all instances at this node is at most 2k, because it's a nice measure. It's like semi-additive. So if we do not put some x into predecessor, it had this x has measure at most k here, and we do not put it into this predecessor, so it has measure at most k here. That means that here this x has measure at most 2k. Yeah.
Could you repeat the definition of the measure? I missed it.
Yeah. Yeah. So this is the definition. For x0, we consider this line.
The minimal covering. Okay.
And it's minimum cover. Okay. Oh, yeah. here we know that this measure is not so big. And after we do this operation, that measure of everything is at most k, because everything that has measure above k we put into this node and erase from our universe. Okay. Oh, I still have time. Great. Now we want to show that this measure will satisfy our properties. So we will put lots of instances into some node, and we cannot put many instances into the same node. Both of the statements are not so hard, surprisingly. First, domain of first lemma, the domain of mu is large enough. Well, what happened? We erased some instances from our universe. So in the end, we have some rectangle in the root of our communication protocol that contains all instances that was not erased during this process. So using this property, we know that measure of everything, even in the root, after we finish this process, is small enough, is at most k. So consider the rectangle in the root. And consider covering of any line here. We pick any x0. If this rectangle is empty, we are done. We map everything. If it's not empty, we have some line. And consider some covering of it. We know that this covering is small enough. Otherwise, we do something wrong with construction of our mapping. And what does it mean that we have a small covering? This covering corresponds to clauses of our formula. That means that there is some subformula of size at most k. And if we plug in x0 into these clauses, we still may violate all of these clauses by Bob's variables. That means that this line, so here, all instances violate some clause from our subformula, from our small subformula. What is the situation here? So we have subformula. So it's at most k. We have x variables. We have y variables. We consider some assignment here, and we know that we still have possibilities to violate these clauses by y variables. Well, how many different assignments to y variables may violate one of these k clauses? It's not so big. It's like k over 2 to the delta. If you pick like random assignment to y variables, it will violate one of these clauses with this probability. So k clauses, and each clause may be violated with this probability. So we are happy. Our k is smaller than 2 to the delta. Okay. Maybe questions, comments?
So the k is smaller than 2 to the delta because your delta is bigger than log n? Is
Yes.
that
Yes, yes. The delta is approximately log n. So k is smaller. And in some sense, this step may be fixed even for constant log n CNF, but next step I don't know how to fix. This is not bottleneck for proving lower bounds. So we are done with this lemma. It's enough to show the last statement. That actually we cannot put too many instances into single node. And for doing it, expansion property will help us. What do we know about our random CNF formula? We know that the dependency graph is like amazing graph. So here we have our constraints. Here we have X variables. Here we have Y variables. And we may assume that any of these two graphs are expander graphs. So we know that for any small set of coordinates here, we have huge neighborhood into each part of variables. So we have expansion on Alice's side, and we have expansion on Bob's side. This is the property that we want to use. Well, we need to use it somewhere. If we do not have expansion property, potentially our formula may contain local contradictions. So it will be easy even for resolution. So we need property like this to prove like lower bound, and we will use it like here to show the last statement. And here our saving will be like approximately k log k. So for previous step, we need k to be as small as possible. And here we need k as large as possible, yeah, as it should be. Okay. Consider some rectangle. We pick some node from our protocol. And we know the property that a measure of any vertical and horizontal line is at most 2k. We want to count a number of lines that may have measure above k. And we want to count now number of horizontal lines that potentially may have measure above k. And for doing it, we consider some process. So pick the first vertical line. So we pick, and we know that we have small covering for this line. So we have covering of size at most 2k. It's a property of our construction of our mapping. So here is this covering. And we may splitting according to which rectangle we choose right now. We divide axes according to this covering. So now let's consider the first rectangle here. And now we want to focus on this region. Can we find some interesting axis that has big measure into this region? So now we care about this horizontal line, but do not care about the bottom part. Let's consider second vertical line here. For this vertical line, again, we have small covering. Since we have small covering even for whole vertical line, in particular for this part, we also have small covering. It's not exactly free, but there should be some small covering. Again, we split according to this process, and we repeat this splitting until we have height k. So we do k steps of this splitting operation. So let's consider some path. In particular, here we choose like first rectangle for the first covering and first rectangle for the second covering. So we choose like this area on the top. All axes that are interesting for us should not have any covering for small size. So in particular, if we consider axes from this region, from the top region, it should not be covering for this axis if they are interesting for us. Does it make sense? So all axes from this region at the same time have intersection with all of these rectangles, but this line do not fully covered by this rectangle, but by union of these rectangles. That means that for all of these axes, we found at least k number of monochromatic rectangles such that this line intersects with these rectangles. That means that we have a very nice property that this excess should not satisfy the huge fraction of clauses of our formula. For all this interested excess from this region, we found k number of clauses that do not satisfy it for all of them. So if x0 is a leaf, that means that it's in the interesting region for us. Then there is some subformula of size, here should be at least k, sorry, it's a typo. Here should be some subformula of size at least k. We may assume that it equals k, such that x do not satisfy any clause from this subformula. And expansion property says that, oh, in fact, like that means that we do not satisfy any clause from this part of the formula. That means that we fix at least c times k number of variables from our formula. So x's that do not satisfy huge fraction of the formula should fix lots of variables. So lots of coordinates are the same for all of these x's. So this is the fraction of x's that do not satisfy specific set of clauses. And by considering this tree, we split interesting x's into this number of regions. So we consider leaves of this tree. So the final mappings that interesting x's for us that potentially can be mapped into this node should satisfy some leaf here, because there is no small covering for them. That means that there are not so many x's that can be mapped into this node. And this is the whole proof. So we are done. Random log-n CNF formulas are hard for communication problem is hard for DAG-like protocols, and formulas are hard for cutting planes proof system. There are two things that I skipped here. I did with rectangles instead of triangles, but it's not much difference. This step will be a little bit more tricky, since we need to choose these lines in the right order for doing it, but there is no other differences. The process will be exactly the same. Yeah, and this is the bottleneck step here, because like we have a huge number of leaves that is approximately k to the k, and we need the property that k is huge, not k, like this c is more than like log k in order to run this process. So this c is an expansion parameter in our graph. So this c depends on the degree of the graph. So this c should be like bigger than log k. This is the bottleneck that I do not know how to fix.
Formally defined bottleneck argument.
Oh, you mean the whole idea of the proof? The bottleneck is just an idea that we want to define this mapping that satisfy these two properties. Yeah. And bottleneck from the proof, I mean to the improve this lower bound for constant CNF formulas. I mean that here this is the only step that I don't know how to fix in this strategy. So all other steps are fixable.
The proof of this lemma is very similar. It feels very similar to the proof of the monotone switching lemma.
Yes.
And that's the monotone switching level, which
Oh,
you use
okay,
to get
yeah.
the symmetric method of approximation.
Yeah.
And there, the k to the k is the same bottleneck why we can't
Yes,
get to the.
yes, it's the same.
So it's really the same bottleneck in both proofs. This is my
Yes.
question. Okay.
Yes. Okay. So more questions about everything here?
Can you remind us what is X and Y, given we're in CNF?
And we'll remind what?
Capital X, capital Y, which you described on the previous slide.
Oh, it's like instances from Alice's side and instances from Bob's side. So it's sets of assignments to these variables and sets of assignments to these variables. It's all possible assignments to these variables and this variables.
Yeah,
So it's like sets of size like 0, 1 to them.
Yeah, then the question is, how do you partition the variables?
If you have like a random formula, then you can make partition uniformly at random. So you give like half of variables to Alice and half of variables to Bob. And after that, you assume that your formula will satisfy this expansion property. Well, it's not okay. It's like true for random formula, for random log n formulas, but it's not true for constant formulas. But we can somehow get rid of constraints that we don't like by closure trick, if you're familiar with that. So we can do it even for constant random formulas. So general idea that we distribute variables uniformly at random between players and do some fixes afterwards if we don't like the distribution. More questions?
You mentioned another number. What's the number of clauses that you can have in this model?
Oh, here
Here
there is no much difference. We need like we need to have expansion property, and our lower bound depends on this R parameter. So the more clauses you have, the worse R parameter here you will have.
At some point they will break it.
Oh, it's at some. It's after some point you break expansion property. Yeah. So I didn't really count, but around the threshold of unsatisfiability, it will be fine. And if you will even go beyond the threshold, it still be okay.
But you need to do it for triangles.
Yes. No, it's not harder. It will be like harder to convince you that it's the same. But for triangles, the only difference that here we need to order these vertical lines and choose these vertical lines in the right order. I don't want to do it right now, but it's the same.
Yeah, okay. That's if they're in morphic systems, but generally I think triangles is something even more.
Yeah, it works for everything where we have this reduction to deadline communication. Okay, yeah, some open problems. First open problem is pseudo-random generators. We heavily use this fact in this computation that clauses are really hard to violate. We need to assign all variables wrong to violate some clause. But what if we have like balanced constraints? So let's consider Nissan-Wigderson generators. So we have n variables and m output bits. So delta is the left degree. P is some predicate that we have here. So to compute output, we want to compute this predicate P on the neighborhood of this output. And we want to pick any point outside of image of this function. And we want to say, is this formula hard for cutting planes? So our strategy do not work for such formulas, even for naive encoding. Like there's a form. In general, we need to consider a bit trickier encodings of this formula, but even for naive encoding, these are variables, and we encode each output bit separately without worrying of anything. Our strategy do not work for balanced predicates. And here we want to have our lower bound for all points outside of the image. So our predicate should be balanced if we want to prove this lower bound. It's a bit tricky question for proving this lower bounds, because usually typical hard example is parity here. But we know that for parity, it's not true. For parity, we have upper bound. And we don't know anything else. My conjecture that, of course, inner product should be hard here. Like, I'll be happy even if you have here logarithmic degree. So we don't know how to deal with balanced predicates at all. It's interesting because, yeah, we have upper bound for parity, and that's canonical hard example for other proof systems. And these formulas are also related to the question NP versus to P poly. So if you can prove the statement that NP doesn't have short circuits inside this proof system. For cutting planes, we don't know. For resolution, polynomial calculus, we know some kind of this result, but not for cutting planes. Okay. Well, other questions, well, pseudorandom generators for other encodings. It's not the only way how to encode pseudorandom generators, and encodings are really different with different properties. In particular, for some encodings, we can prove lower bound for constant depth Frege. For some encodings, resolution is the best what we can do. Well, next questions are more or less famous. So constant random CNF formulas. This technique also do not give us anything. And the last open problem, so separation between cutting planes and monotone circuits. I mean, any technique that do not give us any lower bound for associated function. From this technique, we still can consider these DEC-like protocols, and we can create some general reduction. But now we do not need to care about nice description of the function. We can apply some generic reduction, and for generic reduction, we will get some lower bound for monotone complexity of some function. But we still don't know if it's necessary or not. So yeah, any separation will be interesting. So that's it. Thank you.
Thank you. Any questions? No questions to Dimitri. I think we had a lot of questions already, and it was a great technical talk, and I think people understood mostly. So let's go to lunch, and I think we meet at 2, I think. So let's thank Dimitri again.